To continue our out of order journey through chapter 8, we are going to pick up in 8.3, looking at the product and quotient theorems. Now, product is our answer to a multiplication problem. Quotient is our answer to a division problem. So with these product and quotient theorems, we are learning how to multiply and divide any two complex numbers. All right, so for our product theorem, we're told that if I have two complex numbers, and notice that my first number, they're both in polar form, RCIS theta. My first number has subscripts for 1. My second number has the subscripts 2. If these are any two complex numbers in polar form, and I want to multiply those two numbers together, all I have to do is multiply the moduli and then add theta. Add the two arguments together. So when I'm trying to multiply two complex numbers together, I do that by multiplying the absolute values, those modulus, the moduli, and then I add the values for theta. Multiply their absolute values and add their arguments. Now, multiplication is just repeated addition. If I want to do 5 times 3, that's the same thing as 5 plus 5 plus 5, 5 3 times. Multiplication is just repeated addition. Okay, couple of examples for our product theorem. If I want to multiply together these two complex numbers in polar form and then write the result in rectangular form, well, I start by multiplying those moduli together, those absolute values, and then I add the argument. So I've got 120 plus 30 degrees here. And notice I switched from my long form of the polar form to my shorthand form, CIS theta. So that gives me 20 CIS 150 degrees. And I don't want to stop there because I've been told to give the answer in rectangular form. So I'm going to go ahead and pull this back out into the longhand version so that I've got 20 cosine 150 plus I sine of 150 degrees. And I split it back apart just to remind myself, to make it very clear what it is I need to do here. Since I'm not stopping at polar form, this is fine if I'm able to stop in polar form, I'm done here. But if I'm not stopping in polar form, if I need to go to rectangular form, then I have to plug in what I know. Well, 150 degrees is one of my special angles on my unit circle. It's in quadrant 2, so cosine is negative and sine is positive. So I plug in what I know. Cosine at 150 is a negative square root 3 over 2. Sine at 150 is a positive 1/2. And then I distribute 20 inside my parentheses. Multiplication distributes across addition, so that when I simplify, I get a negative 10 square root 3 plus 10i. And that is the product in rectangular form. Okay, let's go again. We're going to find the product of two complex numbers in polar form. To find that product, we are going to multiply those moduli, the absolute values out front, and then add the arguments. So my moduli here, 3 times 2, and then I've got CIS of, my arguments are 45 and 135 degrees. So the product of these two complex numbers is 6 CIS 180 degrees. If I could stop at polar form, I'd be done. But I was instructed to keep going. So since I need to go to rectangular form, I'm going to go ahead and rewrite this so that I can look at it a little more clearly. Cosine of 180 plus I sine of 180. You don't have to do this step where you write it out in longhand again. That just is to make sure that we're all clear on what I'm doing. Well, 180 is one of my quadrantals. Cosine at 180 is a negative 1. Sine at 180 is 0. and anything times 0 is 0. So this just comes out to be -6 in rectangular form. All right, so that's my product theorem. Now let's look at our quotient theorem, where multiplication is just repeated addition. Division is just repeated subtraction. So if I did 15 divided by 3, that's the same thing as 15 minus 3, minus 3, minus 3, minus 3, etc. I'm just subtracting out 3. How many times can I subtract 3 from 15? Well, I can subtract 3 from 15 5 times, and it gets me to 0. All right, for my quotient theorem, I have two complex numbers in polar form again, where they're not equal to 0, because that not equal to 0 is important, because my quotient theorem, quotient's the answer to a division problem. It sets it up so that I have that second number as my denominator. I can't divide by 0. To work with my quotient theorem, instead of multiplying the moduli, I divide. And instead of adding the arguments, I subtract. So I'm going to divide those absolute values and subtract the arguments, because division pairs with subtraction. All right, let's do a couple of examples with our quotient formula. So we want to find this quotient where I'm dividing the two complex numbers in polar form, and again, I'm moving my answer to rectangular form. I'm not going to leave it in polar form. So my quotient theorem says I'm going to divide those absolute values, and then I'm going to subtract my arguments. So numerator minus denominator. Since I'm subtracting a negative here, minus a negative becomes plus. I add the opposite. 27 divided by 9 is 3, and my argument, 45 minus a negative 180 or plus 180 is 225 degrees. Again, that's a special angle. So since I'm not stopping in my polar form and I need to move to rectangular form, I know that I'm going to need to find cosine and sine function values of 225 degrees. 225 is in quadrant 3. So both of those are going to be negative. The 225, that is my 45 degree angle, my reference angle of 45 degrees in quadrant 3. So cosine is a negative square root 2 over 2, and sine is also a negative square root 2 over 2. And when I distribute the 3 inside the parentheses, I have a negative 3 square root 2 over 2 minus 3 square root 2 over 2. And let's stick that you know what? I could put it in the numerator, but I can also put it down here at the end, since I don't have to worry about it disappearing underneath my radical. There's my rectangular form for this quotient. Another practice problem. Again, I am dividing out those absolute values, the moduli. That means I'm subtracting the arguments. Negative 60 minus 150 in degrees gives me 2 CIS of a negative 210 as my argument, negative 210 degrees. That's my polar form, but I can't stop there. I'm instructed to go on to rectangular form. Well, where is a negative 210 degrees? Let's take a look at that, because positive 210 is here in quadrant 3. I've gone 180 and 30 degrees more. It's that reference angle 30 degrees in quadrant 3. That's positive 210. I need to move negative 210 degrees. Well, since it's negative, I need to move clockwise. This would be a negative 180, and 30 degrees more takes me to negative 210. So negative 210 is coterminal here at 150 degrees. I'm in quadrant 2, so my cosine function value is negative, and my sine function value is positive. And I distribute that 2 inside, I get a negative square root 3 plus I. And that's my rectangular form of this quotient. All right, our last example here, we have these 4 problems, and we're told to work these with a calculator. That's my hint that I am not going to be dealing with special angles. If I'm dealing with special angles that show up in my unit circle, I give exact values. If it's not a special angle, it doesn't show up on my unit circle, then I can't give exact values. I have to use my calculator. And if I'm using my calculator, I've got to make sure that when I'm using trig functions, those function buttons on my calculator, sine, cosine, tangent, or their inverses, I've got to make sure I'm in the right mode. So A and C are both multiplication, I'm finding products, and they are in degree mode. B and D, I'm finding quotients, and they're both in radian mode. So let's go through and look at these. For A, where I'm finding the product, I am multiplying the modulus of each, those absolute values, and then I need to add the arguments. And I need to go to rectangular form. So in my calculator, 2.8 times 5.4, that comes out to be 15.12. CIS, well, what's my argument? 38.5 and 74.5, that gives me 113 degrees. Like I said, this is not a special angle, but it is, I can tell that that's going to be in quadrant 2, right? 113 degrees is past 90, so I'm in quadrant 2, so I expect that my cosine value, that first number is going to be negative and the second number is going to be positive. So I need to distribute this 15 and 12/100ths into my CIS of 113, cosine and then sine. I'm in degrees, so I need to make sure, yep, I'm in degree mode. So I've got 15.12, and then I'm going to start by finding cosine of 113 degrees. That comes out to be, and let's keep 4 decimal places. I think that's what we did last time, 4 decimal places. So if I round that to 4 decimal places, 907, and that rounds to a 9. So that's a negative 5.9079 plus, and then I need to do the 15.12 times sine of 113. So 15 12/100ths times the sine of 113 degrees. I'm in degree mode. That should be positive. Yep, there we go. And I'm going to round this one to 4 decimal places as well, which means I've got to keep that trailing 0 to keep that 4th decimal place. 13.9180i, because that's my imaginary part. Now, I didn't take the time to rewrite this in long form. If you need to do that, absolutely do that. All right, let's look at this next one. I'm going to go ahead and divide out the moduli, or the absolute values out front. And then I need to subtract the angles. This should be CIS. I got distracted and was talking and not paying attention to what I was writing. So I've got CIS, and then I've got the difference of my theta values. Ooh, look at that. Those do not have the common denominators. I'm going to need to come up with common denominators. What are common denominators for 6 and 4? Well, I can rewrite both of those angle values, those radian values, in terms of 12ths. So let's do that. 6 times 2 is 12, so I multiply 2 in my numerator. That would be 10 pi 12ths. 4 times 3 is 12, so I multiply that 3 into my numerator. 5 pi 6th is the same thing as 10 pi 12ths. Pi 4th is the same thing as 3 pi 12ths. So when I'm doing my quotient theorem, I'm subtracting numerator minus denominator. Need common denominators because I'm subtracting with fractions. Okay, 11.37 divided by 3.79 gets me 3. So that's nice and simple. So I have 3, and then I've got CIS. 10 minus 3 is 7. So that's going to be 7 pi 12ths as my argument. 7 pi 12ths. Well, where does that fall on my unit circle? 7 pi 12ths. It's just bigger than 6 pi 12ths, and 6 pi 12ths would be pi half. So an angle of 7 pi 12ths is going to be right in here in quadrant 2. And once again, my cosine value should be negative, and my sine function value should be positive. I'm going to transform this to rectangular form. This is my polar form, but I need to put it in rectangular form to finish out the problem. this is a radian value, so I've got to change my mode to radians. So I've got radian value here. I'm going to be multiplying 3 times the cosine first of 7 pi 12ths. So I've got 7 pi divided by 12 as my argument in radian mode. And this is what I get. It's a negative value. That's what I was expecting. I'm going to round to 4 decimal places. My sine function value should be positive. So I'm going to have 3 times the sine of 7 pi 12th. And yep, it came out positive, rounding again to my 4th decimal place for consistency. So I've got 2.8978i. Don't leave off your I because that's my imaginary part of that number. All right, once again, you need to work through the same processes here. I have confidence in you, and I think that you know what you're doing by now. So I'm going to write the results down here. Make sure that you are in degree mode for this problem. We're doing our product theorem, so you multiply and then you add. And then make sure you're in radian mode for D. You're going to get your answer in polar form and then come around and put it in rectangular form.